Yeah, I mean, that's the whole point of a hash, is it's a arbitrary size input, so it didn't matter how big of the word was. It always spits out the same size output. That's a hash, okay? So the idea is that if your little, like we're going to do initially we're going to do a rot 13 hash, all right? So we're going to rotate 13. So it's an encryption algorithm where we're just going to take every letter and rotate it 13 spaces in the alphabet. All right? That's just the super, it's called the Caesar cipher. It's a super dumb, okay? Very easy. And we're going to see that for small data sets, it's going to work just fine, okay? As you get a larger and larger data set, which is where the Bloom filter really comes into play. I mean, that's the whole purpose of a Bloom filter, is to solve a problem that would be very difficult for us to test. Yeah. We'll try to test it, because what we're going to do is we're going to generate a bunch of random numbers and feed it to the murmur instead of and then we'll hash those, because at the end of the day, what you're actually hashing is binary numbers, and that's what we're going to be focusing on today, is this whole idea of bitwise operations, dealing with the zeros and ones associated with our values, not the starting value itself. Even if you looked at, when we look through a murmur hash algorithm, we'll be looking at, in fact, let's just do it, since murmur hash Java. All right. So here, we'll talk about some code while I'm eating. We'll do that. This is always going to put me in good mood. So I just did a Google search on a murmur hash Java. All right. So I clicked on the first one we found here. It looks reasonable enough. We go into source. We'll go into main, and yeah, here's the murmur hash Java file. So in the end, we can even just drop this one file into our project, or copy and paste what's in there and use this stuff. So let me blow this up for us. Is that big enough? Can we understand that? You can read it? Okay, so let me unwrap. Give me a moment. Oh, I love Oh, I gotta. All right. So as we kind of go through here, this person, do they have a 32 and a 64? So here's a function they wrote called hash 32, and then they let's see, they have that's a default seed value. Does this one take a seed value? Oh, perfect. Yeah. So here they have two different hash functions. One that takes a seed value, the other one that doesn't take a seed value. So by seed value, that means that for this is going to be perfect for the the Bloom filter. Bloom filter kind of indicates that we should use multiple hashing algorithms, right? So the example I gave you, I think they don't tell you what kind of murmur, but they use a murmur hash and then an FL4 or something like that hash, something like that. But what we can do with this is we could actually just call their murmur hash 2, 3, 4, 5 times, passing it a different seed value. So we could pass it a 5, a 10, a 15, a 20, and a 25 as the seed value or something like that, and technically be applying different hash functions to it. Doesn't really matter for our set. The whole purpose of the assignment is to focus on this idea of a data structure, which is the Bloom filter, that allows us to determine it's a probabilistic determination algorithm, whether something is probably a member of a set or not. Okay? So we gotta get the first bite in. Hold on a second. We got priorities here, people. Mm-hmm. That's what I'm talking about. All right. So let's do the default one. Yeah, so here's a hash 32. Do they do a hash 64 as well? Yeah, they have a 64-bit one in here as well. Okay. So Oh, the other one just uses the seed one anyways. All right, so let's just walk through this. So this is their function. Their function is going to take in a byte array for data. So for us, if this was our string that we entered in, we're going to split our string up into a bunch of bytes. Okay, instead of being a bunch of chars, we're going to get the byte version of those chars. So each char in Java is 2 bytes, 2 bytes big. But it doesn't matter. Here's the byte array, and here's the number of elements in that array, the length. Okay, and then here's this magical seed value. Doesn't matter, just some number. All right, and as long as it's always the same number, we're fine. Now, these first 2 values, they even say these are not like really magic values or anything. These are known to be kind of good starting points for this hash algorithm. Okay, so they're setting m equal to, now, right off the bat, we start finding things like this to be kind of scary, right? When we start seeing crazy numbers like that, so let's demystify that a little bit. Yeah, it's just a hexadecimal number. So let's do that. Decimal is probably, I think it's like 3 point some billion or something like that. What is that? 1.5 billion, all right? It's 1,540,483,477. Right? So that's the number 1.5 billion looks like this in hex, and it's far scarier, makes you look way smarter when you write it that way, right? Is that a true statement? All right, so scary looking number and then the number 24. All right, so those are 2 starting values. Then they're going to take the seed, whatever that is. And so here's an operator you probably have not seen before. Okay, this caret. How many of you saw this when you were looking at your algorithms? Okay. Okay, what is it?
It's like x to the power.
It's not. Yep, it's not. It's not the power operator. You know what it is, Blade?
No.
You thought it was the power operator too.
I know. I think it's moving. It's moving from. I can't remember the name, but it's moving one byte to another.
Mm-hmm. So this is called the bitwise exclusive OR operator. Okay, bitwise exclusive OR. And let me just show you what that means here. So let's open up our. So bitwise exclusive OR in our world. So this guy is bitwise XOR. So if I had the number 110101 and I had the number 101111, and we applied the bitwise exclusive OR to that, what we do is we actually do this on each individual bit. So 1 exclusive OR with 1. Exclusive OR says 1 or the other, but not both. So this is a 0, this is a 1, this is a 1, this is a 0, this is a 1, this is a 0. So this would be the answer for that. Make sense? All right, so that's how we do a bitwise exclusive OR. Whenever you see the single ampersand, this is bitwise AND, not to be confused with logical AND. The double ampersand says both of these are Booleans. The bitwise AND says these both are binary numbers. Okay, so bitwise we do an AND on a per bit basis like we just did, like we just saw. And then we have the single, this is the bitwise OR. Make sense? So that's kind of what those guys are doing. But at the end of the day, just mathy stuff, okay? So what are we doing here? We're taking whatever the seed value is, and we're doing a bitwise exclusive OR with whatever the length of our array is. From our perspective in here, what does that mean? We're taking one binary number, we're taking another binary number, because it's going to assume both of those are binary, right? Seed is binary and length is binary. Even though we took them in as ints, Okay, they came in as integers for us. In Java, an int is a 32-bit binary number. Okay, so even though we didn't convert it to binary or anything, Java's kind of smart. It can figure it out, right? It does the conversion for us. So what does it do? It takes the binary number, the 32-bit binary number seed, and exclusive ORs it with a 32-bit binary number length. And you get an answer. And that's getting stored inside of a variable called h. So the variable called h is going to be some 32-bit number. Make sense? Okay, some 32-bit number. More than likely, the first bunch of buckets of it are going to be zeros because they're going to be a whole bunch of padded zeros. Because, you know, the number 8, for example, is going to be what? Just a couple of binary numbers on the far right with 29 binary zeros before it, just padding it out to 32 bits. All right, so in any case.
How to write x to the power y? Now you made me confused.
How in Java?
Yeah.
Math.pow. Math.pow. So this guy.
Haven't you using last example?
Yeah, durr. You dummy. So if you want to say math.pow 3 to the 4th power. So this is what you think is that.
I think last assignment, I did one assignment. Oh, the math.
I think I said it the other way.
The math only I use it.
Love Portillo's. So good.
Made me sick for food.
Yeah, well, I started off sick, so I'm good.
No, I'm sick.
Just for future reference, this is how you get extra credit. So you guys are just kind of aware. I don't know if you saw, did you see on Facebook my class from the other day? One of my students got me, so I had one student that needed to take a day off early for Thanksgiving break because they were flying home to Cincinnati. So they brought me back cans of Skyline chili. Have you ever been to Cincinnati? You know, if you ever go to Cincinnati, it's kind of like Portillo's. They have a local brand thing there called Skyline chili. Yep. Yeah, they have a local thing there called Skyline chili where it's basically spaghetti with chili on top of it. That's their specialty there. But it's like the chili recipe is like a unique, famous family secret recipe type thing. So it might be in a couple other surrounding places, kind of like Portillo's is coming up here, but it's a Cincinnati thing. But yeah, I mean, so he brought me back cans of Skyline chili, so I got those. That was a bribe. And then another one of my students got me this. It's called the Bubba Keg. It's a I'll show you a picture of it. It's a coffee mug. Yeah, here was the picture on that was the picture on Facebook of the mug. And just to give you a little perspective, that's that mug in my car seat.
The size.
So it's a 70-ounce coffee mug. 70. Yeah. So I got that. And then 10 minutes after that, Dr. Locklear brought in my iPad Pro. So it was like Christmas. Yeah. Yeah.
I have a question. Like last semester, in 8501, right? They were giving iPads.
Oh yeah.
This time around, they did not give no iPads.
Hmm.
No tab, no iPad, nothing.
Mm.
Yeah, it happened last.
Yeah, last year, last semester, it was not this semester.
I don't know. Email Dr. Locklear, find out.
I didn't have that.
Say, hey, what's up?
Where's my iPad?
The whole reason I came here was for a free iPad.
Yeah, I did that course.
What kind of crap is this? All right. Let's go back here. All right, so ultimately, what do we get here? Some 32-bit number.
Yeah.
All right, that's our punchline. Get rid of all the scary math. We get some 32-bit number in H. What do we get here? well, we get another 32-bit number in length 4, except it just happens to be a fourth of, using integer division, a fourth of the length of our byte array. Okay? So that's just part of the algorithm for the murmur hash. Just divide it by 4. Here, that's just because. All right, so now we're going to go through a fourth number of times. Whatever the length is divided by 4 number of times. And we're going to start doing some stuff. What are we going to do? We're going to set
What does final mean?
Final means it cannot be changed.
Oh, it's a constant.
It's a constant, but that's right. It's a constant.
Okay.
All right, so we're going to set this integer I4 equal to 4 times whatever I is. Okay, so that expands it kind of back out. Then what are we doing? We're having a variable k, and we're going to take whatever bit lives in that bucket, and we're, because remember that's a byte array.
Mm-hmm.
So we're going to take actually whatever byte lives in that bucket, and we're going to bitwise and that with FF. Okay. 256. 255. All right, so this is the ones place, this is the 16s place. So this is 16 times 16 squared, or plus 16 squared. Just do the bitwise and. So we're going to get some 8-bit number plus some other 8-bit number. And then this guy right here. Do you know what this guy is?
Oh, it is moving a bit with 8 moving left.
It's a left shift. Left bitwise shift. So
there are 3 instead of 2.
3 is a unsigned shift. And I think it only goes one way. I think you can only get 3 going to the right. I don't think this exists. I think just that exists. So as an example here, and you'll see what I mean here in a second. So as an example, when I do a bitwise shift, if I say 11011 left shifted 2, let's say. Okay, what that's going to produce for me is 01100. I basically just roller coastered this guy to the left, dropping off these first 2 things and replacing them on the end with 2 zeros. Does that make sense? But now let's think about what that ultimately did. By shifting it left twice, what's the starting value? This is 1s, 2s, 4s, 8s, 16s. This is 24, 27, 28. Is that right? 1s, 2s, 4s, 8, 16. 16 plus 8 is 24. 27, 28. Okay, so this is
31 minus 4.
1, 2, 4, 8, 16. 16 plus 8 is 24. Plus 2 is 26. Plus 1 is 27. Okay, 27.
Actually, 31 minus 4.
So this is 27. This is what that started off with. This is the 1s, 2s, 4s, 8s. So this became a 12.
Yeah.
1, 2,
8
4,
plus
8, 12, yeah.
All right, so it shrunk it down.
8, 12, yeah.
Mm-hmm. All right, so that's what the bitwise thing does. So this is shifting at 8. This is shifting at 24. So we manipulate those, right? So in the end, what are we going to get? K is going to be equal to some 32-bit number, right? Some 32-bit number. Then what are we going to do? We're going to take that number and we're going to multiply it by the 1.5 billion, that guy, to give us some 32-bit number. Then we're going to, this is the bitwise exclusive OR with itself. So we're actually bitwise exclusive ORing it with itself, which effectively gives us a new number with only the places that had a single 1 in it. So if we K bitwise OR with K. So here, let's just go back to the bitwise guy here. Yep. So if we had 1 1 0 1 1 and we bitwise or exclusive OR that with 1 1 0 1 1, what are we going to get? We're going to get 0 0 0 0 0. Okay. And then once we have those zeros, what are we doing with it? We're right shifting. This is the unsigned right shift R number of times, which is, in this case, is 24.
It says 0 field right shift. Shift the right and the field with 0.
Yep. So really, this field is actually 32. 32 zeros. So since we're doing 24, or right shifting 24, we're going to have that. So we'll shift it, popping in 1s on the other side, giving us some number. Okay? Then we'll multiply that number by 1.5 billion. Then we'll multiply our H, which was up here, that's our seed times length, by the 1.5 billion. And then we'll do a bitwise exclusive R of those numbers. Punchline here, what's happening is K and H are becoming modified versions of what they used to be. They're new 32-bit numbers. All right? And then here's the whether or not there's a couple of extra bits in the array in case the length of your array was not evenly divisible by 4. That's what this is really saying. If that's the case, do some shifting of those guys. But in the end, what do we have? H exclusive OR with A. This is another right shift of the 0 field, right? And then this is H times M. And then this is a right shift of 15 of the 0 field. And then finally, we'll just return H. Noticing that H has been, things have happened between H and K and all that stuff. So our final hash is H, which is going to be some 32-bit number. So this guy returns an int. The 64-bit one should return a long. Yep, because that's a 64-bit number. Make sense? That's what a murmur hash does. We basically just keep rolling the dice, but we have to roll it in the same way. That's the important thing with a hash. All right. So what we're going to do is we're going to start off with kind of a simple hash algorithm. All right. But what we're going to do is we're going to require that our inputs to our program have to just be numeric, letters of the alphabet. So I can do a ROT 13, just so we can explore that a little bit. Okay. So let's go ahead. Fatal configuration problem. Low disk space. Perfect. All right, so I'm going to go ahead and I'm going to close this project. We're going to start a brand new one. And we're going to call this guy BloomFilter. Call it BloomFilter Android. And we'll put it on the desktop, that's fine. All right, and we'll do the normal crap that we did before. And we're going to start off with a blank activity. Actually, I said blank activity last time, right?
Yeah.
Yeah, let's do empty activity. Maybe that'll keep that extra crap off there for me. But the little email dealie, you can remove it pretty easily. We'll leave our main activity name as main activity. That's pretty common. But if you're building out an application that maybe your first screen's a login screen, you might call it login activity or something like that. But we'll just keep rolling with this. All right, I require another bite. Give me a moment. Mm-hmm. Okay. So we should have, I believe, let's go into our resources, layout, activity, XML. Yep, we already have Hello World in there, so let's go ahead and just run this real quick and just make sure everything's zigging and zagging the way it's supposed to be. I did leave my emulator open last time. Okay. So let's start off by writing a little ROT13 cipher. Okay? So we're going to write our app to take in a single input, just a string. We're going to need that in a little bit anyways, right? And we'll read it in and we'll apply rotate 13 to it, where we take every character in the string and we rotate it 13 characters in the alphabet. Okay? English alphabet has 26 characters in it, so encryption and decryption are equivalent. Okay? But the one thing to understand for hashes is hashes, by definition, are one-way ciphers. So that means we cannot unhash a hash value. After we've done all the jumbled up crap to it, there's no way to go back. All right? So hashing is actually often used for authentication. Because what ends up happening is when somebody, and this is why if you ever go onto a website and you forgot your password, you should lose respect for the place if they send you what your password is. Because that's bad. That's not secure. Most places will let you reset your password. And it's not because they're trying to be doing right by you. It's because they don't know what your password is. Because in their database, your password is stored as a hash value. So when you type in your password to authenticate, what they do is they hash your password and compare the two hash values to each other. Make sense? That's how they're actually authenticating you. They don't know what your password is. They can't go and look up your password. So if you've ever been on a website that has a place that sends you your, give us the email address, we'll send your password to your verified email address. If they know what your password is, that's probably a problem. All right. Let's see, what's this guy complaining about? Missing styles. Is the correct theme chosen for this layout? Use the theme combo box above the layout to choose a different layout or fix the theme style reference. Okay, so theme. So we'll do the device default theme. Perfect. Couldn't have written it better myself. Perfect device layout theme. All right, so. Oh, there we go. Much better. Okay, so now let's go ahead and let's get our text box in there and get reading some stuff in. All right, so we'll go ahead and I can zoom here, can I? Doesn't matter. All right, so let's go ahead and we'll give ourselves a large text. That's what I actually, that's not what I want. I want edit text, right? Text fields. Well, we'll use this for our label. Large text. Enter a word. Perfect. And then we'll go ahead and we're going to get a.
How about to hide the bottom slide to make it bigger?
The who? Oh, this guy?
That slide,
Is there
yeah. The next one, if you go
This guy that minimizes it, and then I bring it back by this.
The same way you. And when you click run, it will come back.
Okay, so we're good. We're happy. All right. So we're going to go ahead and give our text fields here. Probably a person's name is going to be a good one because that's going to limit us to. So this configures itself to be editable, but also I think only gives a keyboard that only allows you to put alphanumeric characters in it. We'll find out, but that's kind of what all these different text fields are. They're specialized versions of plain text. They even say on here, this guy is what, a thin veneer, I think I just saw it say. It's a thin veneer over the text view that configures itself for whatever. So I'll go ahead and drag this guy out here for our name. All right, and the text that we'll just leave that in there for right now. And we're going to say word text. Let's just do it word TV for text view. Take the text out of that guy, and it'll look like that. And then I'm going to go ahead and well, actually, I'm not going to worry too much about formatting and stuff. So we'll say enter a word, we'll pop that in there, and then we're going to go ahead and give them a button so we can have something happen as a result of that, that word. So where's my buttons at? Here's my button. And we'll tell this guy we'll say hash for right now, right? And we'll say hash button. Oh man, this is looking sick. We could put this on the App Store when we're done. This guy right here. Now, did you guys have fun with the assignment?
Yeah.
With the Android side? Like a little bit of a ramp up to get it all working on your machine and stuff like that, but then after you had it working, was it fun?
Harder to debug.
Harder to debug?
Yeah.
Okay, so let's go ahead now and go into our main activity Java. And let's give ourselves access to that. Well, let's go ahead and create a listener for that button. So we're going to have a public void hash button pressed. And this guy will take a view v as a parameter. Okay.
What does that view mean?
It sends himself in. I'll actually show you here in a second. So when we click that hash button,
Yeah.
he will pass himself in as that view that called this. So we say view v because it's generic. Everything, buttons, labels, all those guys are views. So that's why we can take a view there as a baseline. And what does this guy want me to do? So this is that shift enter? Doesn't it want me to do something?
There's only sometimes they need to do out.
Because I assume it wants to import the Android view thing. But am I missing something on how to make that happen automatically here?
For Windows, that is alter plus enter, but I don't know how we do it.
I think if you move left to the flashlight,
Left to the flashlight.
yeah, move your mouse left. So before the word public, yeah, here. It's supposed to show a flashlight and then.
Oh, well, there is no flashlight there,
And
though.
if you just click, I don't know, somehow it will show you the flash. I don't know.
I think you can't forget about it.
All right, well, we'll go in and let's add it to our code.
Click once, it will show you the flash, or twice.
Here, we just try to run it again. Let's always say the same. Will it fix it for me? Or is it going to continue to scream? Yep, cannot find symbol class. That's just dumb.
So empty is not good. I think for default.
Did I type it too fast maybe? So view, Android view like that? Yeah. Yeah, see, it did it there before I was typing too fast, so I was ahead of Android Studio, I just typed the word view. I didn't let it complete it. If you let Android Studio complete it, then it'll do the import for you. So, guess the more you know. All right, so now I'm going to go ahead and I'm going to grab the name of this guy, the hash button pressed. We'll go back over to our activity main. We'll click on our button. We'll go down to on click. And we'll paste that guy in there. Oop. That. All right, there we go. So now, if I were to do something here, let me go ahead and let me give myself access to this text field first. That's going to be called Word TV. And I'm going to give myself global access to it. So we'll go back to MainActivity, and I'll go ahead and I'm going to create a private variable up here. So private. Not button, it's edit text, right? And this guy is, what do I call it? Word TV? That guy, I think that guy. All right. Oh, hold on. Same problem.
Okay.
Edit text. Okay, we're happy with that one. All right, so.
What I think the blank template it don't have this library if we are using.
Oh, it doesn't matter. This is fine. We're just learning the little idiosyncrasies. A couple things to point out here, since there's less crap that we didn't see last time.
Mm-hmm.
Notice in a very blank activity, we always call onCreate, which calls the app compat activity objects constructor. Forget about that, but we always tell an activity what their content view is. So our content view looks like r.layout.activity main. And actually, interestingly enough, if I go into layouts, we only get one for these now instead of having that layered approach from before. Yeah, I like this better. This gives us more control. Okay, so this just says, this is effectively this dot set content view, telling this activity who their layout is. So in this case, it's activity main. All right, then we're going to go ahead. We're going to say this dot word TV is equal to this dot find view by ID r dot ID dot word TV. All right, and this guy's going to come out as a button. No, it's not. It's an edit text, right? So he's going to come out as an edit text, and now we have access to that dude. Okay? And what I'm actually going to do here, just so you can kind of see how this works to kind of answer your question, is when we click that hash button pressed, I'm going to set the text view's text equal to v, what v is. All right, v's toString it actually is. So I'm going to say this dot word TV dot set text, and I'm going to set it to v dot toString. Yeah, it's going to show a memory address, but you'll see it's a memory address of a button. Because Java's memory addresses kind of show you that it's a button or it's a, it's a string, it's an integer. It's part of Java's special syntax for memory addresses. Like when I first showed you guys about memory addresses, probably in the last class, the 535, when we created an array and printed out the array showing the memory address. In Java, the first part of the memory address of an array is I square bracket, integer array, if it was an integer array. Okay, so let's go ahead and run this, and this will show you that the button indeed passes himself into this function, letting him know that I'm the one that called this, because we could potentially put our hash button pressed function on multiple buttons on clicks. We could have 5 buttons, each having the same callback function. So now we might be interested in who actually called them, right? Is it button 1, button 2, button 3, button 4, button 5 that actually called this guy? All right, so we'll go ahead and just click hash, and we see, let's spread it out more.
Not a longer enough?
Yeah, it must be Android support widget button something or other. Okay.
Wrong again. Does it has the text around?
Layout with, where's text? Well, let's just see if it fits since we're not doing this long term or anything. I do have to say, Android's a lot better than it used to be. It used to be really bad. Yeah, you could pretty much see it, right? App compat button. So it's letting us know who called that guy. Okay. Similarly, let me actually, I think I could probably even show you, just steal this real quick. I'm going to go back here. Doesn't make a whole lot of sense, but I think that we can click on a label. So I set that text view equal to it as well. So now this guy's on click, and I hope he has a default listener fee. I'm hoping I can click on that, and it calls the same function. But if he's not clickable, we'll put something else out there that's clickable. I think it is. I think it's part of view.
The property has a clickable property.
Oh, and we actually keep seeing how Android applications work because we keep seeing the, there's app compat text, there's app compat button. See that? So we can tell who called that function depending on which kind of animal we clicked on. And they're all views. That make sense?
Yeah.
I do have to, this is way better than it used to be. Yeah, I might start doing some more stuff in Android now. I mean, it's not as good as iPhone. Clearly not as good as iPhone yet, but improving.
But what do you mean by how bad it is? For example, before what?
Oh, it was doing what we're doing here by just dragging stuff out and just was not possible.
Okay. We cannot do.
Yeah, I mean, it acted like you should, but no, it did not work this way. You would mess with it for a long time.
So it means Android Studio is even much worse than Visual Studio.
You mean Microsoft's Visual Studio? Oh, definitely. I mean, Visual Studio, I would say, is a pretty good product in the big scheme of things. I mean, in fact, that's probably what, there's so many people that are like Microsoft language fanboys, C# fanboys, something like that. And there's also a project called Xamarin. I don't know if you're familiar with it, but Xamarin is a cross-platform mobile application development tool set that you can do out of Visual Studio for writing iOS, Android, Windows Phone apps using C#. So instead of it being based on Java, you do it in C#, but you have one code base. So you write your app in C#, and it deploys to Android, to iOS, to Windows Phone. So it's a cross-platform tool using a fairly powerful language, but also using enterprise development tools. So you can get Xamarin for Mac as well. Xamarin has their own studio. I haven't used it. I say I haven't used it. I downloaded it one time and used it for 10 minutes or something just to mess with it, but have zero experience with it. But they have something similar to this for working with it. I don't know if it's better or worse from a design perspective. But then if you're on a Windows platform, you can actually do Xamarin. I think Visual Studio is Xamarin aware. So I think Xamarin is built into Visual Studio. So you can actually create cross-platform mobile applications for iPhone and Android devices from within Visual Studio, which is Microsoft's IDE. And that's considered to be a pretty good tool, Microsoft's IDE. So I don't think that there should be any animosity with that guy.
See that Microsoft start to change its strategy in general.
Well, they have to.
Yeah.
I mean, in the mobile market, Microsoft has to change because they've lost that battle for the operating system.
Yeah.
And I don't think there's any coming back from that. I mean, I think there's as close to a 0% chance as there can be of Windows Mobile ever dominating the mobile.
Android?
Yeah, I mean, it's never going to overtake Android or iOS.
Practically not possible.
Huh?
Practically it seems impossible.
Right. It's as close to impossible as it could be. But because they have such a big development community on the Windows side, and because their developer tools are considered to be pretty good, I could see a majority, or I can see them gaining traction in the market of being able to say a large number of apps that are on the iOS or the Android App Store were created using Visual Studio. I could see that as still being on the table if their tool gets good enough. And I frankly, I don't have enough experience with that tool to know where it's at in its evolutionary phase. Okay, I just know that Xamarin sounds good on paper, but most of the tutorials I've watched make it look fairly complicated. I don't think it's that easy to work with Xamarin. In general, I'm not a fan of cross-platform. In general, I like writing native applications. So I get yes, you have to write the stuff twice, but you get full control over the language and that kind of stuff. And is that a truth, or is that inexperience on my part not giving the cross-platform things a chance? But there's been several situations where I've tried to kind of teach myself a cross-platform tool, and they're just clunky. I haven't had a good experience with them, but at some point I'm probably going to teach a special topics class in our undergrad program using Xamarin just to force learning it, and you'll probably then see the good and the bad from it, and it then becomes part of the problem-solving thing. In general, what I recommend to people regarding cross-platform stuff is if your app is a fairly simple app, utility type, like what we're doing here, these type of things, using a cross-platform tool probably makes the most sense if you do want it to be on all the platforms, right? Because those are simple apps, the interfaces are going to be relatively easy to design. C# is a perfectly good language, so it's not like anything about avoiding C#. I think you can actually make a pretty good argument that C# is better than Java. Because really C# was able to take most of its cues from Java. Microsoft tried to steal Java first. Some microsystems sued them. Microsoft then had to come out with C#, which said, okay, well, we have to create a language of our own anyways, so why don't we take all the good stuff from Java and let's fix a couple of the things that Java broke. So we could really say C# is an evolution of Java. Fair enough? It's certainly not fair to say C# is a bad language because Microsoft made it. There's too much animosity between these different companies where you have the Microsoft fanboys and the Apple fanboys and the Java fanboys. All these languages are perfectly viable, right? So whatever. So I already took the on-click off of this guy. So let's go ahead, and what I'm going to do is I'm going to go ahead and create another class for our hash. That way we kind of have a landing place for when we go to do our hash here in a little bit. So I'm going to write our rot13 in there. So I'm going to go ahead, I'm going to right-click on this. We're going to say new Java class. And we're going to name this guy hash central. All right, so it's going to be called hash central. I guess in Colorado that might have a strange double meaning, wouldn't it? You get that? Isn't hash, isn't that what they call marijuana?
Yeah, hash.
Why do you know so much about this? Yeah, my wife and I went on vacation to over fall break to Colorado. She wanted to see the mountains and stuff. And now since I've come back, whenever I'm carrying a cup of coffee, one of my other students who also seems to know a whole lot about that industry.
Yeah, it's called same. Hash.
Okay, yeah. Well, he calls it Colorado coffee. So I guess that's a thing there, spiking coffee with THC or something. I don't know. I didn't find any places selling spiked coffee there, so I think on paper it's far more of a people think it's one thing, like it's Disney World of pot. It's not like that. You couldn't walk into Walmart and buy marijuana in Colorado. It didn't feel like that at all. Okay, so in any case, we're going to create our little hash central, and we're going to write a static function here. Static string rot13. And this guy will take in a string s. All right, and what it's going to do is it's going to go through and any character it finds, any numeric character, I'm sorry, not numeric, any alphabetic character it finds, it's going to rotate 13 in the alphabet. Okay, so what I'm going to do here is I'm going to create a string lowercase is equal to I get it? HIJK. And then we'll say string uppercase is equal to lowercase dot to uppercase. All right, so now I have the upper and lowercase alphabet. Okay? So now we're going to go ahead and we're going to start walking through our string. So we're going to say string answer. It's going to be empty string. We're going to be building a new string. So we want to ask the question, is the character I'm currently looking at in one of these guys? Is he in lowercase or is he in uppercase? If he's in one of those guys, we'll go ahead and do the rotation. Otherwise, let's just keep it. We'll just leave it alone. So that way we'll allow spaces and numbers and question marks, but we won't touch those. We won't change those. Okay, so we're going to say for int I is equal to 0, I is less than s dot length, I plus plus, and we'll go ahead and say if s dot char at I, so that character, and actually I'm going to do this real quick. This, let's say, if lowercase dot index of s dot char at I is not equal, well, let's say if it's, well, not equal to -1. That means it was found in there. Okay, so it exists in the lowercase alphabet. Else, it's in the uppercase alphabet. Do that. Else, answer plus equals s dot char at I. We'll just keep it without modifying it. Okay, so if it's lowercase, then we need to go ahead and we need to rotate it. All right, so what are we going to do? We're going to say answer plus equals lowercase dot char at lowercase dot index of s dot char at I. That's going to give us that index plus 13 mod 26. All right, so let's say we were looking at an F. All right, so this is at bucket what? 0, 1, 2, 3, 4, 5. So we found it at a 5. So 5 plus 13 is 18, right? Okay, so we're going to add to that 5, 18. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we're right there. So that's at bucket 23. 5 plus 18. Is that right? Yeah. Okay, so that's at bucket 23. So then we're going to take 23 mod 26. How many times does 26 go into 23? 26 goes into 23 0 times with remainder 23. So that's our position. But let's say I started with a T. Okay, I started with a T. So that's actually, hold on, let's start with the X because we already know where that is. That's 20, it's 23. Okay, that's 23. So now we're going to add to that 13. So 23 plus 13 is 36. How many times does 26 go into 36? Once with remainder 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the K. So it should wrap to the K. So that is, for here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It is the K. Make sense? That's why we're using the mod to do the wraparound. Okay? So that's how we get our answer if it was in the lowercase. Same answer if it's in the uppercase, except we'll pull from upper. All right, else we'll grab our answer. Finally, after we go through all of them, we'll just return answer. Make sense? So that's rot 13. So now what we'll go ahead and do, let's go back to our code here. We're going to say enter a word, we're going to say hash, and then let's go ahead and give ourselves a our output. Ruh-roh. I told you we shouldn't have done this. All right, we'll give ourselves our output.
Because of gravity,
Hey.
you should say let the length become the
Yeah, as long as we keep everything tightly packed. Otherwise, if I want to do spacing, it goes the other way. But this is fine. So we're going to call this guy answer TextView.
Yep.
All right. So that's our answer there. So let's go back to our code. And we're going to go ahead and give ourselves that text view. So we'll say private text view answer TV. Yeah, I probably wouldn't have called this guy Word TV since he's an edit text. I would have called him Word ET, but yeah, I'm just going to leave it. So that's answer TV. Then we're going to say this dot answer TV is equal to the text view version of this dot find view by ID r dot ID dot answer TV. Okay, so now we can go ahead and read in our text that was in our box. When they hit the hash button, we're going to go ahead and we're going to say this dot answer TV dot set text. And what are we going to set the text to? We're going to set it to hash central dot rot 13 of whatever's in our Word TV. This dot Word TV dot get text. All right. I think we can also just convert it to a string. Is that not right? We do have to use toString? Let me see this here real quick. What does this guy return? He returns WordTV.getText returns something called editable. Yeah. Okay. So we'll go ahead and set our answers text equal to whatever our hash central returns when we pass to rot 13 our WordTV get text. Okay. So we should see a jumbled up version of that dude now. That's running. I should get the Italian beef going. The second course. Oh, that just looks awesome. Huh? Oh, yeah.
You like it more?
All right. So we'll go ahead and enter our word. We'll say hello world. And so we should see a space in the middle of our output. So there's our hash. There's our space in there. Okay. So there's our hello world hash. And just to give you an idea on how ROT13 works, just to show you this, I'm going to create another label. We'll call this guy, I don't know, let's call it answer 2 or something for right now. So I'm going to throw a, actually, will let me copy this. Was it match parent? Fill parent? Match parent? Oh, he's dropped inside of something else here. All right, we'll go with that. So we're going to say decrypt in there. Let's call this guy decrypt. Whoa. What did I do? It's going to be called decrypt TV. All right, so you'll see kind of how this works. I'm going to call this one encrypt up there just so we can kind of see the labels there. All right, so let's go back to our Java here. We will private TextView decrypt TV is going to be equal to this dot. This is the TextView version of this dot find view by ID of our dot ID dot decrypt TV. All right. And then what I'm going to do here is when we hit that hash button, I'm going to go ahead and let it set the answer TV's text. But then what I'm going to do is I'm going to say this dot decrypt. Woo. Zigged when I should have zagged. Decrypt TV dot set text to this dot, this dot hash central dot rot13 of this dot answer TV dot get text dot toString. So that's what's nice about ROT13. You encrypt and you decrypt with the same function. So I encrypted it by calling ROT13. And then I'm going to take that encrypted version that's stored inside of answer TV, and I'm going to decrypt it, storing it inside of decrypt TV by passing it the exact same encryption function. That's the convenience of ROT13. But with that comes some insecurity, but we should at least see this. Let's go ahead and run this. Oh yeah, look at that. Mm-hmm. All right, so we'll do hello world. We'll click hash. There's our encrypt, there's our decrypt. Make sense? All right. Now, so any questions about that stuff? So we're going to use our simple little hash. Let's go ahead and let's convert. Well, we're saying this is a hash right now. But ROT13 actually is not a hash. Why? Based on what I've told you about hashes, why is this guy not currently a hash?
It has to return a fixed length of stuff.
Yeah.
And where is the by the input?
Right now, what length of stuff does it take? Or what length of stuff does it return?
The length of the input.
Right now, whatever the length of your input was is the length of your output, right? I.e. not fixed length. So we want it to be fixed length. So let's create. Let's go into our hash central. And we're going to do static string ROT13. Whoa, hold on.
Now you call it a hash.
And we're going to create our ROT13 hash. All right, so I'm just putting another function inside of our hash central called ROT13 hash. And what's this guy going to do? He's going to guarantee a fixed size output. Okay? So now for our little world here, we have to decide how many, what's the bit size of our hash. And actually with Bloom filters though, it's not the bit size of the hash, it's the number of unique values it can hash to, right? So when we looked at the, so the example there would be, they had a murmur hash and an FL whatever hash, FL4, FLV, whatever it was, hash algorithm, and it would give us these like single digit numbers, right? Their numbers on the example were between 0 and 14. Let's go ahead and bring that up. Okay, so that means it was a 15-digit possible output. If the output was some number, the hash value was some number between 0 and 15, guaranteed. That was the output of the hash, was a number that was between 0 and 15, which means in this little example, we only have 15 unique hash values. Is that correct? Isn't every value going to hash to something on this?
If you give any input, then there will be either 1 or 2.
That's 6 and 8. I'll bang on the keyboard a bunch of times. That's 0 and 4. It always gives a number between 0 and 14. That's my output. Okay? So the number of unique hash values in this case is 15. Not very secure, right? If we have a really large data set, having just, so if I should be able to send in thousands of inputs here, right? Thousands of inputs. But two things, so here, I got a murmur 4 there. Let's see if I can get a murmur 4 from something else. I got an FNV4. So this guy hashes in FNV to the same value as this guy hashed in murmur. All right, so there's kind of a light collision there.
Yeah.
If that makes sense. In this case, the number of hash values hash functions we used was 2. All right. Part of that is because they limited, so a hash has a arbitrary size input and a fixed size output. Okay, where the output is the number of the largest value we can have. Okay, so if we're going to go with something like this, we're going to have 15 bits. Or I'm sorry, 15 possible buckets for output, 15 unique outputs. That means the biggest, how many bits does it take to get to 15? It's the ones place, the 2s, the 4s, the 8s.
Yeah.
So 8 plus 4 is 12, plus 2 is, plus 2 is 14, plus 1 is 15.
It's about a million.
Oh, 4 bits. 4 bits.
4 bits.
4 bits. Come in here. Let me show you. to have 15 unique outputs, we need a 4-bit number, 1111, 0000. This is the number 0. This is the number 1, 2, 4, 8. So this is the number 15. Okay, so this is actually going to give us 16 unique outputs, right? Okay, so maybe that's the easier way of doing this. If we wanted to force it to be 15, then we would have to disallow a 0 in that case with the 4 bits. But let's just say 16 unique outputs for ours. That way we don't have, so that means literally our hash function takes in an arbitrary size input and always spits out a 4-bit output. Whatever size input we want, we can give it 10 gigabytes as an input string, and it will spit out a 4-bit output. It's not a very good hash function, but it is a hash function nonetheless. That make sense? All right, so we need 4 bits from that guy. So how do we create something that is 4 bits big with our little hash? Okay, well, a couple different things we can do. We could just do a normal thing and then only grab the last 4 bits, right? Yeah, so maybe we do that. And let's see. So even one character is 16 bits. So one character hash is going to be, we're going to be okay with that. Yeah, so I guess let's just roll with it. Go back into this. Go in hash central. So let's take in a ROT13 hash along with int numbits for how many bits are we want it to grab. So what we're going to do is we're going to go ahead and we're going to say string answer is equal to hash central.rot13 of s, whatever was passed in. So that'll get us our hashed value. All right. Then we're going to go ahead and we're going to take our get our bytes from that. So we're going to create a byte array called the bytes, and this is going to be equal to answer dot get bytes. Get bytes. Okay. So now we only need half of the last bytes. Does that make sense? All right. So now what I'm going to do is I'm going to say, let's see, let's say, actually this guy, that's fine, we can return a string. No, actually let's return an int. So we're going to say int value to return is going to be equal to the bytes at bucket, the bytes dot length -1. That's going to give us the last byte in that guy, very last byte, but we only want half of that. Okay, we only want the last 4 bits. Okay, so that means that I don't want the leading numbers to mess it up. So what can I do? Can I right shift 4? If I right shift 4, if I have a number like this, 3, 6. If I had a number like this, okay, that's 8 bytes, or 8 bits rather. 1 byte, 8 bits. So I'm currently dealing with a number like that. I need to somehow massage that into a 4-bit output. So if I right shift 4, I'm going to get 0, 0, 0, 0, 1, 1, 1, 0. That make sense? That's the number I'm going to get. Now, I don't care that this is 8 bits because I know that the value is going to be limited to those 4 bits for the value. Make sense?
Yeah.
So we'll go back into here and we'll take that and we're going to right shift 4. And then we'll go ahead and return value to return. Oh, I missed the return. All right, so let's see what this guy looks like now. So instead of calling rot13, we're going to call rot13 hash, and decrypt is now off the table. Okay, because we're only using 4 bits of what has to be a minimum of an 8, even if I give it 1 character that I want it to hash. Okay, 1 character is a 16-bit value. Okay, so in the best scenario, I'm destroying 75% of my value. Okay, in most scenarios, I'm destroying 99% of the value. I'm only keeping 4 bits of my hash value. Okay, we're not rebuilding this. Okay, if a car gets blown up in an explosion, okay, and we have 0.0002% of the car left, we can't rebuild the car from that. All right, so understand that we have a weak hash. This is a weak hash. So instead of doing rot13 here, we're going to say rot13 hash, where we're going to take in the string that we want to hash, this guy, as well as, in this case, we're going to say 4, which actually that means I wrote this a little bit funky.
Yeah.
Instead of 4, I want to do it on num bits, right? So I want to shift it num bits. We just happen to pass in a 4 for num bits. Who?
8 minus num.
8 minus num bits? No, because we know we have 8.
Okay.
We know that's 8 bits.
I thought you want to remain how many bits in hash. The num bits is like how many num bits we want to keep.
Oh, well, I am, but I'm returning it as an int. So I'm returning 32 bits. I just happen to know that all but 4 of those bits are zeros. Because it's only possible to have that in this case. Right? Because I know that if I were to look at this number right here, only 8 of those bits could possibly be non-zero. Everything else before that's going to be zeros, because that's a byte, not an int. A byte is 8 bits.
Yeah.
So, and just to kind of, if you guys are missing that, these two numbers are the same, 1101 and those are the same number. Okay, so it doesn't matter how many zeros you put in front of it. That's just, we're representing the number, what, 1, 2, 4, 8, the number 13? We're representing the number 13 in this footprint rather than this footprint. Make sense? Okay. They have the exact same value, though. Okay. We're playing around with 32-bit numbers just because that's convenient for us, is to play around with 32-bit numbers. But we know that when we get a number out of that byte array, it will be no bigger than that. That's the largest value we can get out of that byte array. All right, and when we take that number and we left shift it 4, we're going to get that. But when we put that number inside of an int, we're going to get, so let's see, I need to do 24. We're going to get that value. And that's what we're actually returning. So even though we've put it in a gigantic shoebox, we still know that the maximum size value that's coming out of there is a 15. Does that make sense? So, and let's see if that's true. So now in our main activity, we'll go ahead and call rot13 hash, passing it whatever our word is, whatever we type in, as well as the number 4, and we should always get a value back that's between 0 and 15. That's the hope out of this guy. Mm-hmm. Whoa. Hold on. Something zigged when it should have zagged. Couldn't execute for...
No use at all this error message for debug.
Just get rid of decrypt here because we're not going to need that. That guy still has an on-click set as that dude. This guy does not have an on-click. Let's make sure that's not where it broke. All right, so that looks fine. So then we come back over here. Let's run this again. Wonder if something weird just happened.
Hash, maybe something. We no longer have this guy, I just deleted him. Okay. All right, so it is, I think it's getting into that function. Let's just make sure that's the, oh. This guy comes out as an int. We have to turn him into a string to set the text. It's hash central, this guy returns an int, okay. So there's a 7. Put some more stuff on there. Still a 7. The last.
More stuff.
It's still there?
I think it's because I'm hitting the same keys over and over again. There's a 6.
I think it's based on the last chart.
Oh. Epic. All right, so I guess one thing we could do to always apply it the same way, we can probably add a little bit more randomness to it this way. Instead of getting the last byte, we could get the byte at bucket, the bytes.length divided by 4. Let's say divided by 2. Just the byte in the middle-ish. It's either going to be the middle or one off the middle, depending if we have an even or odd number of bytes. So now we should get a better randomness to our bytes because it's not always going to be based on the last one. But, oh, actually, hold on. You're well, empty string, we'll just let our program break because that means we're not hashing anything. This should be okay, but actually I don't know if it's going to be substantially better. So there's our 7. Let's give it some real words. Hello is a 7. Hello world is a 2. Woot is a 6.
Nice.
LOL There's also a 6.
It's a
So
sentence
woot
rule.
woot and LOL are collisions. Oh, because of the O in there. 15 is a 3. 18 is a 3. Oh, because
it's a 1.
yeah, from the 1. All right. So in any case,
If you put a 1, what do you? Okay. Well, it's because of 1.
elephant. So 7.
It becomes P.
Yeah. But now we can get more random here if we do something like this. Well, basically, we can make our ROT13 hash substantially better than it is if we give it more bits. We can give it up to 8 bits without changing anything, but if we want to do like 32 or 64 bits, something like that, then what we can do is we can go through here and have every value. We can concatenate bytes together to give us a larger number to do shifts on. Okay, but you know what? We can actually do something even better with this. We can do a byte array. Would that work? Actually, might work okay. So let's get our hash value. Well, right now it's not going to make any difference. We can just say this is an acceptable hash value. It's giving us numbers between 0 and 15, just not real random ones. Okay? All right, so we can go back and we can add new hashes in here later on if we'd like. So now let's go ahead and let's start building out our set. We want to be able to put values into our set of strings. Okay, so part of what I want to do with this is we're going to have a let's see. Let's start off by putting those guys into just a collection here. So that's already our encrypt. So let's give ourselves a vertically scrolling. All right. I'm going to get rid of this stuff for a second. All right, so height is going to be unset. I just get it below everything. Okay, let's do that. And the ID will be, we'll call it the list. I'm going to show you how to do a list view. Just throw something new in there. I'll have to go review it because we have to use our array adapter thing to do it, but I pretty much know how it works. Okay, so let's go ahead and give ourselves access to this guy in our code. So I just created a list view. Grab this guy and put it out there. All right, and so now I'm going to go in here to our main activity and we'll give ourselves access to that dude. So we're going to have a private list view called the list view, and we'll say this dot the list view is equal to the list view version of this dot find view by ID r.id dot the list. Okay. And actually, let's change this to be the list, and change this to say the list. Keep the variables consistent. Okay, so now we need to go ahead and we need to create an array adapter. So let me just Google that real quick. Android list view example. Basically, we're going to fill up an array and then connect that array to that list view to give us our stuff. Right. Array adapter. That's the equivalent to data source on iOS. Create a simple list view. Let's just leave it this guy. All right, we want to have our array of values. There's our list view, and then we're going to have a new adapter of strings. Okay. All right, so do we get simple rows? Just check something here real quick. r.id dot, actually it's r.layout dot support simple note. Layout dot simple list item. Okay, yeah, we have to create our own. All right, so we're going to come in here to layout. We're going to go to new layout resource file. All right, yep. All right, then we can choose what kind of layout we want it to be. Those are qualifiers. I think there's a way to give a simple row layout. Let me go back here. All right, so they have this simple cursor adapter. What's that dude gonna do? Create. Yeah, we still have to do our simple. We have to do our list item. we able to do this? Let's see. See if I can cheat a little bit. So this guy gives us a list. We do have something in here like a list row, I think. Yeah, table row. No, I don't think that's going to do what I want it to do. All right, so I'm going to create a new layout here. We're going to do a new layout resource file. The root element is going to be a table row. And it's going to go in the, and we're going to call it it's going to be a simple simple table row. It's going to be the name of the dude. So I'm just creating a new XML document here for our simple table row. And that guy is going to be a type table row. And I don't think I actually have to do anything at this point. I don't think I have to do anything with him. We'll find out here in a second. We just had to make sure he existed. All right, so now I have my list. I'm going to go ahead and create a string array called vals. And let this guy be equal to a new string array. Let's just put 20 things in there for right now. For int I is equal to 0, I is less than vals.length, I plus plus. And what will we do in here? We're going to go ahead and say vals at bucket I is equal to, let's say, the word number followed by a space concatenated with I. So number 0, number 1, number 2, just a whole bunch of strings. Okay, then we're going to go ahead and create our array adapter. We'll go ahead and go back to that sample code because that guy uses a string array as an example. So list view there. Okay, so that's our string array vals. So here's our adapter. It's going to be an adapter of strings. So let's just we'll say we're going to have an array adapter of type string. Let's call this guy the adapter, and this is going to be a new array adapter of string. And the parameters this guy takes looks like it's the activity, the layout, and then the name of the, looks like the text value in there. So I need to give that, looks like I do need to give that guy a text value. So let's go back here real quick, simple row. We'll go ahead and throw in a large text. Oh, hold on, sorry. All right, so this guy's already a let's take this out for a moment. So we're happy again. And then if I put large text in there now, it's not happy. Oh, because it wants me to choose a style. So we're going to go with device default. All right, now it's happy again. And we're going to call this guy's ID, we're going to call it row text. Just so he has a name. So our simple table row is going to have a single text view in it called row text, and I'm going to actually spread that out across the whole thing. Just do a simple version of this. All right, so this guy takes the activity that's associated with this, then the r.id dot, actually it's r.layout, right? Layout dot simple table row. Then it's going to take r.id dot row text. And then what does it take in the last spot? Then it takes the actual values we're putting in there. So for us, it's called vals. They called theirs values up here. Ours is called vals. Comma vals. So there's our array adapter. And then we can go ahead and say this dot the list dot set adapter to the adapter. All right, so now the working theory is, so I filled up an array of things. I created an array adapter around those strings. That array adapter is going to use the simple table row layout we created, which has a single row text in it. And I'm going to pass it the values I want to put in there. So let's see if that's enough to give us a list view rather. All right, so there's our list view. So now what we want to do is as I type in words, let's add it to a list view. Okay? But let's see, do I need to... Yeah, we can do that. So I'm going to go ahead and say private array adapter of string. We're going to call this guy the adapter. And then down here, instead of creating our values, we'll make this guy empty at first. Actually, let's just get rid of that. So we're going to go ahead and say the adapter is equal to a new array adapter, telling it who his row is, what text to fill in, and then we'll go ahead and give it a new string array of size 0 to put in there. I think that should create a blank adapter. Let's make sure that's the case. So this should run but give us nothing in our list view right now. Okay. And then in here, let's go ahead and say this dot the adapter dot add, and let's just keep adding our words. So this dot word TV dot get text dot toString. And let's see if that actually adds it or if I have to tell the list to update itself. I think I'm going to have to tell the list to update itself. This dot the list dot update view layout. Refresh. Drawable state. Let's try it without it, then I'll have to look it up. There's got to be a way for us to tell that list view that there's new data, go ahead and grab it. Do we need to update our adapter every time?
By the way, does this function know the adapter? It's not a global variable.
Yeah, it does. I made it global.
Oh, sorry.
Let's go back in here. Let's look at array adapter. Oh, I can give it something of type list of objects. Oh, actually, we don't even have to give it the original collection. It can create an empty collection for us. Restores, okay. Let's try that. This looked kind of funky anyways. I think by giving it that original thing, it made it a fixed size. So I'm not necessarily expecting text to pop in there now because I don't think it's going to do that, but we expect it not to crash. Oh, wait a minute. Oh, it does. It does update it automatically. Yeah, that. Okay, so and actually then can we actually get our values out of our this dot the adapter dot get. Yeah, we can get the item out of position. Okay.
We can choose it.
All right, so we're going to go ahead and store every string we put in there into our adapter, and then we're going to go ahead and get our values here. So right now we're setting the hash value, but really what we want to do is we need to set the Bloom filter, right?
Mm-hmm.
So our Bloom filter we've decided is going to be a 16 bucket array.
Yep.
Okay, because we're using 4 bits, 0 to 15.
Yes.
So 16 bucket array. All right, so let's see how we're going to represent that. Let's say private. In array. What's this?
I told him I made my array 1 million bucket.
So
Oh, did you?
so it's impossible. You should make a negative positive.
Like,
A false positive. It's quite hard to make. I just made a 10 bucket.
Yeah, ours is going to be a 16 bucket array. Okay, for our 4 bits. Make sense? All right, so that could hold the numbers 0 through 15, or our legal values in there. Okay, and we're going to go ahead and initialize it to a bunch of zeros in here. So we'll say, here, I'll show you a couple of tricks. Is it arrays.fill? And I'm going to fill this dot the Bloom filter with zeros. So there's more magic tricks you have access to. So here, there's a class that exists in Java called arrays, and it has a function called fill that takes in all sorts of different kinds of arrays and will fill it with an initial value.
Oh.
So rather than me writing a quick for loop that goes through all the buckets and putting each bucket I is equal to 0, bucket I is equal to 0, bucket I is equal to 0, this guy just does the same thing.
So it's
For us.
like initialize.
Yeah, he fills it with zeros, but he's not doing anything that we couldn't do ourselves in 3 lines of code.
yeah.
The for loop is written inside of this function. Okay, but be aware that it exists. And in general, you know, like when I look at your guys' assignments, when you see that I've complained about things, I usually don't give you a hard time about stuff like that. I give you a hard time about like things that you couldn't know. Hey, oh, and by the way, look, we've used generics. So this array adapter, instead of holding generic objects, he holds strings. That's what that syntax is. Okay, so he holds strings, and that allows us to, when we added something to it, we added this guy. The add function expected this dot, the adapter dot add. It expects a string now because we use a generic to create them, telling him to expect a string. As opposed to if I take that generic off of here, we'll take it off of there, we'll take it off of here. So now it's a generic array adapter. And I do add, look what the add function takes. The add function expects me to pass it an object. He doesn't know that it was generically specified to hold strings. That's what generics is. We were able to build the thing in terms of, the people who built it as a generic data structure built for holding generic objects. But through the generics keyword, or the generics syntax, we're able to specify the kinds of values we'd like it to hold. That way, when we put stuff in, it can expect a string without us having to cast it. And when we take stuff out, it'll come out as a string without us having to cast it back to a string. As it stands right now, I don't have to use generics. I can add things to it, but if I go ahead and I say get item at position, notice he comes out as a generic object rather than a string. Even though I know he's a string. If I threw a string in there, I know when I get him back, he's going to be a string, but he's a string in costume, and he looks like an object until I cast him back.
How do you write a class of generic object?
How do you support the when you implement the thing, you'll implement it with something that looks like this. Question mark that says this guy is allowed to be constructed with a generic.
Okay. So if I write my own class, which is a generic class, actually I don't specify what's the data.
Correct. You're setting it up as a generic. Yeah, the class is a generic because it can accept different types. All right, so array adapter, and usually generics are built on top of things that are already generics. So there has to be a beginning. So for instance, an array adapter is built on top of a linked list. And the linked list class that's built into Java supports generics. So at some point, you have to be building your thing on top of something that supports generics. Otherwise, you'd have to invent what it means to support generics.
Yes.
So this guy's going to be a string again. And again, we'll make it a string. So yeah, I mean, generics are really good. They're really powerful. They're really easy. But now you have a context for how they actually work. As opposed to just throwing them into your code and saying, yeah. And it was less about the generics and more about like the hash maps and stuff like that. Some of you have been using hash tables for several of your assignments. All right. So in any case, we have that. We'll go ahead and fill up our Bloom filter here. Then what we'll do out here is right now we're setting our text to our the value that comes out of here, but actually let's just use this value. And we'll say this dot the Bloom filter at bucket, whatever this guy is equal to 1. That'll fill up our array, right? So we'll go ahead and add the string that they entered to our a list of strings, and then we'll go ahead and mark our Bloom filter with the appropriate 0 or 1. In this case, we're only giving it 1 hash, but just to kind of see that it's working, let's go ahead and let's just spend a couple more minutes here, and then we'll take a good break. Instead of our encrypt thing here, let's go ahead and make this guy show the filter. Oh, we'll keep him named answer TV. That's good enough. Okay, so that's going to be our Bloom filter. So we're going to show inside of there what our array looks like. So let's just go ahead and teach our, well, let's do it in here. Inside MainActivity, let's create a private void update filter view. All right, and this guy is going to create a string answer and set it equal to something that looks like that. And in the end, we'll say answer plus equals that. And in the middle, let's go ahead and spin through our Bloom filter and put all the values that all the ones we found in there. So we'll say for int I is equal to 0, I is less than. Actually, you know what? I want to check something here real quick. Arrays dot toString. Oh, very nice. Don't even need this.
That's a long
I think so. Let's see if this works. So we already have our string. So after we add something to our Bloom filter, we'll go ahead and update our Bloom filter. So we'll say this dot answers TV dot set text equal to arrays dot toString of, and we're going to pass it our this dot the Bloom filter. And that should give us some sort of, I hope, visual representation of an array. So right now, every time we add something to our hash, it's going to throw it into our adapter, so we have a new value that's on our list of values that we now know. We'll also run it through right now a single hash, and we'll mark in our Bloom filter at that bucket a 1, right? And then finally, we'll go ahead and update our Bloom filter answer thing to show what our updated filter looks like. So we run this. So there's hello, and there's our Bloom filter. Now let's put in world. There's our Bloom filter. Let's put in elephant. There's our Bloom filter. Whatever. Make sense? Mm-hmm. So filling out our Bloom filter now. We're using a very simple hash. Next thing we'll do is we'll try to determine if something is in our Bloom. That's pretty easy to do, right? So we'll take a 20-minute break, then we'll come back and we'll look at that piece. Sound good?